Normally, something exploding inches from your face would be the worst part of your day. In a high-speed crash, it's the thing that saves your life. Getting a human body safely to rest from highway speed has to happen about a tenth of a second. And today, we're breaking down the exact chain reaction that makes that possible. The sensor that has to make a split-second judgment call, the chemistry that inflates a bag hard enough to catch you, and one mistake in that chemistry that ended up triggering the biggest recall in automotive history. Here's exactly how it's supposed to work and how once it didn't. You might think the seatbelt handles this by itself, but it can't. Not safely. In a hard enough crash, a seatbelt locked rigidly in place would slam your chest with enough force to injure your internal organs. So modern seatbelts use a small torsion bar that lets the belt release, just slightly under extreme load, letting your upper body move forward. That protects your chest, but it doesn't protect your head and neck. Those keep swinging forward on their own, like a pendulum, even after your torso has already stopped. In a serious crash, that unrestrained head motion is exactly what can be devastating. That's the gap airbags were built to close, but it took an embarrassing failure first to figure out how. Airbags were not always explosive. The earliest designs tried to inflate the bag using stored, compressed air triggered by a mechanical spring. It didn't work well. The spring couldn't reliably tell a real crash from a hard bump, and even when it did trigger, compressed air simply couldn't fill the bag fast enough to matter. Neither problem was solvable with that approach, so it never made it to production cars. It took one engineer, working on both problems at once, to actually crack it. That person was Alan Breed. First, he replaced the unreliable spring with a far more consistent mechanical sensor, a small steel ball held in place by a magnet. In a violent enough crash, the car decelerates so quickly that the ball's own inertia rips it free of the magnet and it flies forward to close an electrical circuit. A clean, reliable signal that a real crash is happening. Second, and more importantly, he replaced compressed air with a chemical explosive, sodium azide. That single change is what made airbags fast enough to actually work, and by the late 1980s, Chrysler had begun making driver's side airbags standard equipment, the first widespread commercial use of the technology. Here's exactly what happens inside that canister in the split second after your crash. An airbag doesn't fill up like a balloon on your breath. That would be far too slow. The gas is manufactured on the spot, in a fraction of a second, by a chemical reaction. The signal from the crash sensor reaches a thin wire called a squib, which heats up past 300 degrees Celsius almost instantly. That heat triggers the sodium azide, which decomposes explosively into nitrogen gas and sodium metal. And it doesn't take much. Roughly 50 grams of sodium azide can produce something like 70 liters of nitrogen gas. More than enough to fully inflate a bag under real pressure. The catch was that the leftover sodium metal, which is reactive enough to become corrosive if it's exposed to moisture, so manufacturers had to build an additional compound specifically to neutralize it before the gas ever reached the bag. That leftover byproduct is exactly the kind of detail that, years later, one company got catastrophically wrong. In the late 1990s, one major manufacturer, Takata, switched to a different gas-generating compound, ammonium nitrate, because it was cheaper. Ammonium nitrate turned out to degrade badly when it repeatedly exposed to heat and humidity over years of use. And in some inflators, it began detonating far too violently, blowing apart the metal canister itself and sending shrapnel into the cabin. It became the largest automotive recall in history, more than 67 inflators, and it eventually bankrupted the company. It's a sharp reminder that in a system built to explode safely on purpose, the chemistry has to be exactly right every single time. Today, most modern airbags have moved on entirely, using guanidinium nitrate instead, a compound that produces the same nitrogen gas without sodium azide's corrosive byproduct or ammonium nitrate's instability. The sensor side of this had its own blind spot too. The original ball and magnet sensor could only measure that a hard impact happened. not how severe it actually was. So it occasionally fired for something as harmless as a bad pothole. Modern cars fix that with MEMS accelerometers, tiny silicone chips that measure the exact rate of deceleration, feeding into an electronic control unit that also pulls in data from wheel speed sensors, gyroscopes, brake pressure, and even seat occupancy sensors. That fuller picture lets the car judge not whether a crash is happening, but how severe it is, and adjust exactly how forcefully the airbag needs to deploy. Once triggered, the igniter flies within about 2 milliseconds, and the bag is fully inflated with 20 to 30 milliseconds after that. It inflates hard. The front face of the bag can move toward you somewhere between 150 and 250 miles an hour. That speed is exactly why timing is everything. For an airbag to actually protect you, it has to already be fully inflated by the moment your body reaches it, which is also why airbags in some cars are designed not to deploy at all if you're not wearing your seatbelt. Without the belt controlling your position first, you could be thrown into a bag that isn't ready for you yet. This all comes down to Newton's first law. An object in motion stays in motion unless something stops it. When your car slams into something, the car stops, but your body doesn't. Not immediately. It keeps traveling forward at the speed you were driving until something intervenes. The airbag's entire purpose is to be that something. A cushion that spreads the stopping force across a wide area and slows your body down more gradually than a soft plastic and metal could ever. Stack the whole sequence together, the crash is sensed almost instantly. The igniter fires within about 2 milliseconds. The bag is fully inflated by 20 to 30 milliseconds after that. It stays fully open for roughly 100 milliseconds, cushioning you. Then vents through small holes built in the fabric, deflating on purpose, so it doesn't trap you against it right when you need to move. Between 1987 and 2017, frontal airbags are credited with saving more than 50,000 lives in the US alone. All from a chain reaction that finishes before you've even fully registered that you've crashed. It's a strange trade when you think about it. Something that looks and sounds like a small explosion going off in your face, engineered with just enough precision to be one of the safest things in your entire car. If this made airbags finally click for you, that's the goal of this channel. Breaking down how everyday machines actually work, one accurate explanation at a time. Subscribe if you want more of these, and I'll see you in the next one.